Seismic analysis of multi-story building with and without floating column and shear wall. Abstract. This research mainly concentrates on analyze the behavior of structures and comparing the parameters like story displacements, story drift, story shear, time period. Considering G+20 story building, 4 models. Model I will consider the normal structure, Model 2 will consider floating column structure, Model 3 will consider shear wall structure, Model 4 will consider both floating columns and shear wall structure. The seismic analysis of G+20 story structures is analyzed by both equivalent static and response spectrum method. Using Indian Standard Code IS 1893, Part 1, 2002 and ATABS 2018 software. Obtained story displacements, story shear, story drift, time period for seismic zone 4. 1.2, DL+LL+RSX, load combination is critical and increased displacements in Model 2, decreased in Model 3, 4. The story drift compared normal structure increased drifts in Model 2, decreased in Model 3, 4. The story shear compared normal structure decreased shears in Model 2, increased in Model 3, 4. Comparing all 4 models, the time period of floating column structure I.E Model 2 is greater. Model 3 structure is better performances, lesser displacements, more strength comparing with all 4 models. Keywords: floating column, shear wall, earthquake, story displacements, story drift, story shear, equivalent static method, response spectrum method, high-rise building. Introduction. India is a developing country, where urbanization is at the faster rate in the country, including adopting the methods and type of constructing buildings which is under huge development in the past few decades. As a part of urbanization, multi-story buildings with architectural provisions are constructed. These necessities are nothing but soft story, floating column, hefty load, the lessening in stiffness, etc. Nowadays many urban multi-story buildings have open first story as an unavoidable feature. This is mostly being adopted to accommodate car parks or reception lobbies in the first story. Whereas the total seismic base shear as practiced by a building during an earthquake is reliant on its natural period. The seismic force distribution is depending the distribution of stiffness and mass along the height. The behavior of a structure during earthquakes rests critically on its complete shape, size, and geometry, along with how the story shear are moved to the ground. The story shears at different stories in a building necessity to be transferred down to the ground by the shortest path. Any discontinuity in the structural members results in the change in the load path. Buildings having vertical setbacks bases a sudden variation in earthquake forces at the levels of discontinuity. The discontinuities in the load path is formed in the buildings with floating columns at and middle stories or ground story and do not continue up to foundation. Hence, there is need of understanding the behavior of earthquake, also constructing and developing earthquake-resistant structures. Thus, shear walls are introduced to resist the lateral forces formed during earthquake. They are known as the vertical elements of the horizontal force-resisting structure. Shear walls in the construction counters the effect of lateral loads acting on structure. Specifically, significant for high-rise structures, shear walls thus act against lateral forces produced by airstream, earthquake, and unequal settlement loads. Urbanization and growing of high-rise buildings is the need of current population, and earthquakes have the potential for causing the greatest damages to those tall structures. Hence, it is needed to take into account the seismic load for the design of high-rise structure. Commonly the shear wall building will be strong. But the floating column structure, how behavior with the shear wall will be studied in this study. Floating column. A column is a vertical compression member which starts from foundation level and continues up to top level, which transfers the load to the ground. The term floating column is also a vertical component which at its lower level rests on a beam which is a horizontal member. Structures with columns that suspend or float on beams at and middle level and do not go all the way to the footing, have breaks in the load transfer path. The beams in turn transfer the load to other columns under it. In such columns the loads were measured as a point load. Floating column does not have any structural continuity because they are built over the beam. There are many projects in which floating columns are already accepted, particularly above the ground floor, so that more open space is available on the ground floor. Shear wall. Shear wall is an earthquake-resistant component used to resist the horizontal forces such as airstream force, seismic force. These forces act equivalent to the plane of the wall. Shear wall commonly provided in high-rise building. It will introduced from foundation level up to prolonged to the building height. Shear wall thickness may differ from 150 mm to 400 mm, reduces lateral sway of the building. Rigid vertical diaphragm transfers the loads into foundations. Moment-resistant frame must be provided along the other route to resist strong earthquake effects. Shear wall's behavior depends upon material used, wall thickness, wall length, wall positioning in building surround. Structures that contain shear walls from reinforced concrete are generally prevalent for using in areas and countries that earthquake-prone. 2. Literature review. Hassam el-Sakari, Khaled Galal, 2020. 1. In this work described shear wall structure is a communal seismic force resisting system that is used for both reinforced masonry, RM, and reinforced concrete, RC, buildings. This paper objectives to estimation the quantities of construction materials required for RM shear walls related to those of RC walls. 3 multi-story RM shear wall buildings with different heights located in 3 different cities in Canada were selected. The analysis and design events were frequent for each case when RC material was used. The quantity of structure materials used for the shear walls of each building was evaluated for both RM and RC cases and they were compared. Moreover, the cost of labor and temporary works for RM and RC shear walls was estimated and compared. Maniesh A. Hirewar, E.R. Rahul Satya, 2020. 2. This paper offerings a reliability analysis of multi-story building with floating column by STD.Pro V8I. This study contracts with the stiffness stability of all the story and is proposed to reduce the irregularity presented by the columns which are floating in the building. Modeling was performed through detailed analysis using a commercially available FEM tool, STD.Pro V8I.0. Vishal N., Ramesh Kannan M., Kirthika L., 2020. 3. This paper presents seismic analysis of multi-story irregular building with different structural systems. In order to study the structural behavior of a 20-story building with vertical setback irregularity has been modeled and analyzed by response spectrum method considering with and without construction sequence analysis, CSA, using different structural systems in CSIA tabs V16 as per BIS 1893:2016, Part 1. Analysis has to be done only by sequential application of loads in each story for the safety of the structure and cost effectiveness. Finally, outcomes such as axial force, shear force, bending moment, and response such as story displacement, story shear and story drift are plotted and compared for each structural system. Akshay Gujar, H.S. Jadhav, 2019. 4. This paper presents a building construction with floating column are analyzed in single step by using linear static analysis with declaration that the buildings are having total load once the whole structure built completely. But in real condition construction of building is completed story by story. Therefore that effect due to sequential loading is dissimilar than actual analysis. Objectives of this study is evaluate result of vertical irregularity such as floating column in the buildings. In this paper result of construction order analysis and regular analysis are compared. For analysis the G+10 story structure is considered for Zone 4. The results such as displacement story shear, story drift are obtained by ETAB software. Mr. Ankarvidya, Mr. Shahayajali Sayed, 2018. 5. This paper a research on comparing the seismic effect on shear wall building and without shear wall building. In this paper review of different researchers on the idea of multi-storied building with and without shear wall is summarized. In India, most adopted type of earthquake-resistant structures is with shear wall. These structural walls may vary constructed on their design and utility, and their position in any building plays an important role for resisting lateral force. Kanjakuri Sunitha, Mr. Kiran Kumar Reddy. 2017, 6 In this paper studied on the analysis of normal structure with 5-story, 10-story, and 15-story. And different locations and different situations like floating columns, shear wall, bracings are to taken as similar models. 2 approaches to be considered for the analysis of structure as linear static method and time history method. Seismic analysis done for using ETAB software. Compare the displacements, story drift and the time history values of the different models. In static seismic analysis concluded that the maximum story displacements and story drift values are increasing for floating column. By observing the drift ratio, the deflection and story drift will be drastically changed when the height of the structure will be increased. Vinchkini K., Dr. Rajiva S.V., 2017, 7 In this paper seismic behavior of RC and steel concrete composite multi-story building with floating columns with and without shear walls. This research studied models are analyzed using response spectrum analysis with the assumption that the structure will be subjected to all the loads or full load in a only stretch when the whole structure is constructed completely. The analysis of the building models is done by CSI ATABs. The current study contains response spectrum analysis of RC structure and steel concrete composite structure with floating columns at the middle of penultimate bay, with and without shear walls, and also determine parameters like story displacement, story drift and story shear of RC structure and steel concrete composite structure with floating columns at the middle of penultimate bay, with and without shear walls are compared. Isharohila, S. M. Gupta, Babita Saini. 2015, 8 In this paper studied the seismic response of the multi-story irregular structure with critical positions of floating column. The structure model will be considered as G+5 and G+7 with Zone 2 and Zone V. To estimate the results of the modeled structure as story response, story shear, story displacements will be obtained by the using of ATAB software. The floating column should be avoided in high-rise structure in Zone V. Story displacements increases with floating column structure. Story shear will be reduced when occurrence of floating column because of decrease mass of column in structures. Increase the size of the beams and columns to progress the performance of building with floating column to reduce the story displacements and story drift. 3. Methodology. Consider the multi-story structure as G+20 story, 4 different structure and seismic analyzing structures by using as per Indian Standard Code is 1893, Part 1, 2002 and ATABS 2018 software. To determine the parameters like story displacements, story shear, story drift, time period, the following seismic analysis method will be adopted for the analysis purpose. The modeling of the buildings are done using ATAB software, following the codes is 456-2000, Part 1,2, and is 1893-2002, PART 1. Shear walls are designed as per is 13920 to 1993 Clause 9.1.2 and their thickness is not less than 150 mm. As per is 1893:2002, methods adopted are equivalent static lateral force, or seismic coefficient method. It deals with series of forces which are acting on high-story building to show the impact of an earthquake ground motion. This technique will not show much safer results in high-scale areas of earthquake. As entire design base shear is computed, and then along height of the building it is distributed based as some simple methods appropriate for the regular distribution of building with stiffness and mass. Reliant upon the floor diaphragm action, the obtained design lateral force at each floor then shall be distributed to the individual lateral load resisting element. This is allowable in most codes of practice for regular, low to medium rise buildings. Response spectrum method, it provides a technique for performing an equilateral static lateral analysis. Response spectrum analysis uses similar principle of time history analysis, only the variation is values obtained here are for maximum response. To find out forces, peak displacement readings are more significant. Response spectra curves are the curves strategized between maximum responses of single degree of freedom system, SDOF, subjected to specified earthquake ground motion and its time period. Displacement of story relative to base of structure is called story displacement. Most significant and most clearly evident point of contrast for structure is deflected shape. The displacements of building in different stories for all models have been compared. The results are taken for Zone 4 with medium soil condition. Chart 1 represents the story displacements V/S story in X direction, Zone 4 for the combination of 1.2, DL and LL and EQX. Results will be critical and available from equivalent static method. Observing the results and chart comparing to normal building, Model I, the story displacements is 6.8% increased in Model 2, decreased 30.11% in Model 3, decreased 26.58% in Model 4. Chart 2 represents the story displacements V/S story in X direction, Zone 4 for the combination of 1.2, DL and LL and RSX. Results will be critical and available from response spectrum method. Observing the results and chart comparing to normal building, Model I, the story displacements is increased 8% in Model 2, decreased 46.32% in Model 3, decreased 38.22% in Model 4. 2. Story drift. Displacement of one story relative to other story is called story drift. The story drifts for all models have been compared. Chart 3 represents the story drifts V/S story in X direction, Zone 4 for the combination of 1.2, DL and LL and EQX. Results will be critical and available from equivalent static method. Observing the results and chart comparing to normal building, Model I, the story drifts is increased 6% in Model 2, decreased 28% in Model 3, decreased 22% in Model 4. Chart 4 represents the story drifts V/S story in X direction, Zone 4 for the combination of 1.2, DL and LL and RSX. Results will be critical and available from response spectrum method. Observing the results and chart comparing to normal building, Model I, the story drifts is increased 8% in Model 2, decreased 38% in Model 3, and decreased 32% in Model 4. 3. Story shear. The design seismic strength to be applied at each floor level is called story shear. It is the sum of design lateral forces at all levels above the story under consideration. Chart 5 represents the story shears V/S story in X direction, Zone 4 for the combination of 1.2, DL and LL and EQX. Results will be critical and available from equivalent static method. Observing the results and chart comparing to normal building, Model I, the story shears is decreased 6% in Model 2, increased 28% in Model 3, increased 24% in Model 4. Chart 6 represents the story shears V/S story in X direction, Zone 4 for the combination of 1.2, DL and LL and RSX. Results will be critical and available from response spectrum method. Observing the results and chart comparing to normal building, Model I, the story shears is decreased 6.5% in Model 2, increased 28% in Model 3, and increased 24% in Model 4. Story shear, in absence of floating column M3 shows maximum story shear value in both static and response spectrum analysis, in presence of floating column at model M2 shows minimum shear values. 4. Time period. Time period, when a structure is excited by seismic forces, it starts to vibrate. The lowest natural frequency, f, of vibration of a structure corresponds to the longest time period, t, of vibration, as frequency and time period are inversely proportional. Table 8 Time period, SEC. 6 Conclusions. From linear static and dynamic analysis of buildings subjected to floating column and shear wall, following conclusions are drawn. 1. Seismic analysis of G+20 story structures is done by both equivalent static and response spectrum method to obtain the parameters story displacements, story shear, story drift, time period for seismic zone 4. 2. Considered the story displacements comparing to Model I, increased 8% in Model 2, decreased 46% in Model 3, decreased 38% in Model 4. With increase in story number displacement increase, that is from lower to higher story displacement increase. The multi-story building with floating column undergoes large displacement than model having no floating column. 3. Story drift obtained from equivalent static method and response spectrum method, increased the story drift 8% in Model 2, decreased 38% in Model 3, decreased 32% in Model 4. Structure with shear wall and without floating column shows minimum story drift while with floating column shows maximum story drift. 4. Story shear obtained from equivalent static method and response spectrum method, decreased the story shear 6.5% in Model 2, increased 28% in Model 3, increased 24% in Model 4. Story shear rate will be more for lower floors than the higher floors due to the decrease in weight when we go from bottom to top floors. 5. Compared all four structures, the time period of floating column building Model I2 is greater than all four models. 6. On comparison of the results obtained for each model, it is observed that the building with shear wall have lesser displacements and story drifts when compared with the floating column models. Shear wall structure is better performances, more strength comparing all models. The stiffness are increasing in the with shear wall in corner, L shape, other than floating columns without shear wall.